Hello and welcome. My name is Elhelw. In the last video, we started talking about concurrency control. In particular, we talked about locks and how locks are used. We talked about shared locks, exclusive locks. We talked also about two-phase locking and how we can use that to guarantee that our schedules are serializable. We mentioned the fact that even with two-phase locking, we have some problems or some things that we have to deal with that may happen. One of those was cascading rollbacks. And we handled those by looking at a more restrictive version of two-phase locking, which is the strong, strict two-phase locking, or SS two-phase locking. We mentioned also that there are other problems that may arise, one of those being deadlocks. So we will start by talking today about deadlocks and see how we can handle that, and then we will go on to discuss other lock-related topics. So deadlocks. What is a deadlock? A deadlock is a situation where multiple transactions are waiting for each other. Specifically, they're waiting for locks held by each other. So you would have one transaction holding a lock, and then another transaction is waiting for that lock. But then the transaction that is holding the lock is also waiting for another lock held by another transaction, and so on, until the point where all of them are blocked and cannot proceed any further. So this is what we call a deadlock. This can happen even with two-phase locking, or even with the strong, strict two-phase locking. Let's look at an example and see what that looks like. So let's assume we have these two transactions, T1 and T2. T1 requests an S lock on A, and then reads A, and then requests an X lock on B, and able to write something to B, and then there's more operations. T2 pretty much follows the same sequence, except uses B first, so it wants to read something from B, and then write something to A, so it requests the S locks and S lock in that order. So what would happen to cause a deadlock between these two transactions? Let's look at the timeline. Assuming T1 starts first, so it requests an S lock on A. Since A is not locked at this point, it can acquire this, so now A is S locked by T1, and T1 should be able to proceed. However, let's say the control goes to T2, so T2 now is requesting S lock on B. Again, B is unlocked at this point, so T2 can acquire this lock, so now B is S locked by T2, and T2 is able to proceed as well. Now let's say that T1 starts reading A, that's normal, it's fine. And then it goes to the point where it requests an X lock on B. Now B is already locked by T2, right? Using the S lock. Of course, the X lock that we're requesting and the S lock that's already there, they're not compatible. So T1 has to wait. So now T1 is blocked. It cannot proceed any further until the lock on B is released. So control is going back to T2. T2 is going to read B, and then it requests an X lock on A. But A is locked by T1 using an S lock, which is not compatible with the X lock that we're requesting. So now T2 is also blocked and it cannot proceed any further. So now we have both transactions. Each of them is blocked on the other one. So now this is a deadlock. Neither of them is able to proceed and release the lock so that the other one can complete. So each one of them is holding one lock and waiting for the other. So none of them can proceed any further. So this is basically what a deadlock is. And it could also be between more than two transactions. Like you could have T1 is waiting for T2, T2 is waiting for T3, and then T3 is waiting for T1, and so on. So it could be any number of transactions, not necessarily two. All right, so if a deadlock happens, how do we deal with it? Of course, this is a situation that we need to do something there in order to make things proceed. Generally speaking, there are two ways of dealing with deadlocks. There is something called deadlock detection, and then there is something called deadlock prevention. Deadlock detection is something that happens after the fact. So basically, the system works as usual, and then if a deadlock happens, then the system should be able to detect the fact that there is a deadlock, and if it does, then it needs to do something about it. Deadlock prevention is more preemptive. You try to prevent the situation where a deadlock would occur so that you don't get to a point where it happens and then, try to address it. So these are two ways of trying to deal with the deadlock problem. Let's talk about each of them, see what are the pros and cons of each, and then we can discuss which is better or what's the best situation for either of them. starting with deadlock detection. Deadlock detection, like I said, this is something that the system has to do after the fact to detect whether there is a deadlock or not, and then to do something after that. So how does it detect the existence or the presence of a deadlock, right? Usually we use a graph. We call that the waits for graph. What's the waits for graph? It's a graph where each node is a transaction, and then we put an edge from one node to the next if one transaction is waiting for a lock that's held by another transaction. This is different from the dependency graph that we talked about in the previous videos that we used to determine whether a schedule is serializable or not. It's similar in the sense that each node is still a transaction, but the edges there represented the conflicting operations. Here, the edges are representing the locking and which transaction is waiting for a lock that's held by another transaction. So again, in this case, once we are able to put the edges, we can look at the graph and see if there are cycles or not. If there is a cycle, then this means that there's a series of transactions that are all waiting for each other, which means that this is a deadlock. Let's look at an example to see that in practice. So again, this is the example that we looked at a little while ago. What would that look like in that graphical representation? So we have two transactions, so the waits for graph is going to have two nodes. First, we have T1 is waiting for T2. T1 is waiting for the lock B to be released, and that lock B is held by T2. So since T1 is waiting for T2, we're going to put an edge from T1 to T2 in the graph. But also we have T2 is waiting for T1. T2 is waiting for the lock on A to be released, and that lock is currently held by T1. So we're going to put an edge from T2 to T1 in the graph. This means that we have a cycle in the graph and there is a deadlock. Again, like I said, this could be 3 nodes, 4 nodes. As long as there is a cycle, there is a deadlock. So this is the first part of the deadlock detection. So we have detected that there is a deadlock in the system. First of all, when does that check happen, right? The system needs to do that check either periodically or when it detects that, for example, all the transactions are waiting for one reason or another, then it can make that check. So once it detects that there is a deadlock, it needs to take some action. And this action usually is in the form of choosing one of these transactions to abort or roll back so that the others can proceed. This process is called victim selection. The system needs to choose one of the transactions to be the victim so that the others will be able to continue, and then later on this transaction that was aborted can restart from the beginning and hopefully we'll be able to finish. So the question now becomes is how do we choose the victim transaction, right? There are different options and different things that the database can use. Some of this criteria could be you could potentially choose the victim as the newest transaction. Each of these criteria has some assumptions behind it. So the newest transaction assumes that the older the transaction is, the more work it has done. So the newest one probably hasn't done a lot of work. So rolling it back incurs only a little overhead. Versus if you try to roll back one of the oldest transactions, it's very likely that it has already done a lot of work, so you don't want to waste all that work that's been done. So one option is to choose the victim being the newest transaction. Another option is choosing the transaction with the least number of writes so far. Again, because the one that you're rolling back, it means that you have to reverse any operations that's been done. So if it has already written a lot of information or done some updates and so on, you have to reverse that. So that's going to be expensive. So again, we're trying to minimize the amount of work that needs to happen. So potentially roll back the transaction with the least amount of writes. A third criterion would be to abort the transaction with the most number of locked items. The assumption here being if you roll that transaction back, then you're going to release a lot of locks. So basically this allows many other transactions to proceed. Whereas if you roll back a transaction that's holding just 1 or 2 locks, then it might help, but maybe it doesn't resolve the deadlock completely. So again, this is an assumption that hopefully will help more transactions to be able to finish. Another potential criteria to look at would be the transaction that has the least number of rollbacks so far. This tries to avoid starvation. So basically, if a transaction keeps getting rolled back every time it starts working, then it might get to a point where this transaction is unable to do any work, unable to complete. So we're trying to allow such transaction to complete. So we're going to roll back something that potentially hasn't been rolled back before or has been rolled back the fewest number of times. So this would avoid starvation. Yeah, so that's regarding deadlock detection and victim selection. Now we're going to talk about the other way of handling deadlocks, which is deadlock prevention. Like I said, deadlock prevention is more preemptive. It tries to avoid the problem of deadlocks to start with, tries to prevent the system from getting to a point where a deadlock may happen. There are several techniques for deadlock prevention. We're going to discuss a couple of them here, but there could be also more than that. One technique is to use something called conservative two-phase locking. Last time we talked about the basic two-phase locking, and then we talked about two variations. We talked about the strict and the strong strict two-phase locking. This is another variant, which is conservative two-phase locking. Conservative two-phase locking says that a transaction needs to acquire all the locks that it needs in the very beginning. If any of these locks is unavailable, meaning it's been already held by another transaction, then this transaction will not acquire any locks. It will release anything that it has already acquired. It will wait, and then it will try again later. What does that mean? It means that a transaction will only be able to start working if it has already acquired all the locks that it needs, so it will never need to wait for anyone. If when it tries to acquire locks, some of them are not available, then it will not hold on to anything else, so that we avoid the situation where it holds one lock but is waiting for another, and then someone else is also holding one and waiting for another. So either it has everything it needs or it has none, so that no one else will wait for it. So this will avoid, having the deadlock situation. Of course, the downside of that is we may have starvation as well, because one transaction may try to acquire locks, fails, so it waits, it tries again in a bit, still fails, so it waits, and so on. So it might end up waiting for too long. There might be, safeguards against that. Like, you might also say that if it waits a certain amount of time, then the next time, like, you might add some priority factor in things or stuff like that. So there are ways around it, but this is just kind of like the basic version of this technique. Another deadlock prevention method is using timestamps. Basically, what this means is that each transaction has a timestamp. Usually, this timestamp denotes the time when that transaction started, and then we define the concept of a transaction being older, which means it has an older timestamp. A lower timestamp. Whenever a transaction requests a lock and that lock happens to be held by another transaction, we have to make a decision. We have to decide whether to block a transaction to make it wait, or to abort a transaction. Which transaction to lock or which transaction to abort, this depends on the timestamp of each of them. So let's make some definitions just to kind of like to see how this works. So basically, let's say that thold is a transaction that is currently holding a specific lock, and tRequest is a transaction that is requesting a lock on that same object. There are two variants of this technique, basically two different decisions that we can take. We will explain both, but before we explain both, just want to note that we have to stick with just one of them. We cannot use both of them at the same time within the same set of transactions. We have to choose one of them and stick with it, because that's how we guarantee that there will never be any deadlocks. We'll see that when we explain what these are. The first variant is called wait die. Wait die simply says that if the requesting transaction is older than the one that holds the lock, then the requesting transaction will wait. Otherwise, the requesting transaction has to be aborted. So this means that basically the older transaction waits for the newer transaction. If the newer transaction is done requesting, then it just will get aborted. What this means is that why does this avoid deadlocks, right? So we see here there is a condition for which one can wait for whom. An older transaction, let's say we have T1 and T2, right? If T1 is older than T2 and T1 is requesting a lock held by T2, then T1 will wait for T2. T2 will never wait for T1 because T2 is not older than T1. Only one of them is older than the other. Like the condition will only be satisfied in one direction but not the other. So we will never have this cycle. If T2 requests something held by T1 in this case, then T2 will just end up getting aborted, and then T1 will be able to continue. So if we approach the situation of a deadlock, then one of them will automatically get aborted, and then that situation will resolve itself. So there will never be a case where we have this cyclic dependency of transactions waiting on each other, because it requires one of them to be older than the other in order for that to happen. The same thing is in the other variant of this, which is called wound weight. The names are a little weird, I know, but that's what they're called in the literature. So here it's kind of the opposite. If the requesting transaction is older than the one that has the lock, we're going to abort the one that has the lock. Otherwise, T requesting one was going to wait. So again, the waiting condition is only in one direction. So if T requests, the one that is requesting the lock is newer than the older one, than the one that holds the lock, then it's going to wait. So for it to wait, it has to be newer. So you will never have a situation where two transactions or more are waiting for each other. This way, this definitely guarantees that there will never be a deadlock. So which do we use? Do we use detection or do we use prevention, right? We've talked about deadlock detection and prevention. Detection, like I said, it's something that happens after the fact. After a deadlock happens, the system will detect its presence and then it will act by doing victim selection and so on. Of course, the benefit of that is that you don't have to do constant decision making like we're talking about here. The downside of detection is that when it actually happens, when you detect the deadlock, then you're already too late. Like there's already a deadlock, the system may have been already blocked for some time. You will have to reverse the work, you have to do victim selection. You might choose a transaction as a victim that does not resolve the deadlock, so you may have to choose another one and so on. So there is a lot of overhead when a deadlock is detected. Prevention is more pessimistic. Basically, it assumes that deadlocks are very likely, so it tries to actively work on preventing them. The good thing is that it doesn't need to maintain a wait for graph. It doesn't do victim selection. It just follows one of the two rules that we've talked about before. It might be this is the downside, that it might be a little too aggressive. It might end up aborting a transaction because it thinks that it might cause a deadlock, whereas in reality maybe a deadlock would have never happened. So it might actually preempt cases without knowing for sure that they would lead to a deadlock. So there's a trade-off here, right? Detection, because it's more optimistic, it assumes that deadlocks are not very likely to happen. So that's why we're going to wait until it happens and then we're going to figure out what to do. So it's better to use that if we know that there isn't much interaction or interference between transactions. For example, if the transactions are short and they use only or access only a few objects, so it's not likely that they will access these objects at the same time or request locks on them at the same time. So deadlocks will be not very likely, so that detection could work in these scenarios. But if the transactions are long and need to access many objects at the same time, then it is very likely that deadlocks might happen. So then prevention may become the best option in this case. Aside from deadlocks, I want to switch to a different topic still related to locks. This is called lock hierarchy. Before we get into the hierarchy, let's pose this question. What do we do if we want to do an operation on many objects at the same time? For example, like if we're doing a bulk update, for example, on many rows or all the rows in a particular table, right? So given what we know so far, we would have to request locks on all of these objects. Again, think about the rows in a table. If we want to update all the rows, then we need to request X locks on each row of the table in order to be able to update them and then release those locks at the end. The problem is that requesting too many locks is very expensive. Each lock, like the process of requesting locks and releasing locks, this is handled by a component called the lock manager in the database, right? And it needs to keep track of all the locks that are being held, what transactions are holding them, what types of locks are there, who else is requesting, and people or transactions will be put in a queue so that when the lock is released, those transactions in the queue will get notified, and one of them will be able to acquire the lock and so on. So there is a lot of overhead that is associated with locking, acquiring locks, releasing locks, and so on. So if you are, as a transaction, if you are requesting locks on too many objects, this becomes very expensive. So in practice, things don't work this way. In practice, databases provide locks at multiple levels of objects, and it will choose the level that will allow it to acquire the least number of locks possible. What does that mean? Basically, look at this hierarchy. So the highest level in database is the database itself as a whole. So imagine that you could request a lock on the database. This basically means locking everything inside the database with a single lock. This is not very commonly used because obviously this basically will destroy any concept of concurrency. The one that is very common is locks at the table level. You could request a lock at the table level. So of course a database may have many tables. So each of these tables basically you can visualize it as a tree. A database has multiple tables. You could request locks at the database level or at the table level. Locks at the table level are pretty common. You could request a lock at the table. You want to lock the whole table, especially in operations that involves the full table. Like if you're doing a bulk update on every row in the table, or if you're doing things like altering the structure of the table or dropping a table and so on. At the next level, there is the page level. This is somewhat common, but maybe not as common as the table level. Again, a table has multiple pages. So again, the hierarchy is expanding. The lower we go, the more objects there are. The next level is the row level, and that's super common to acquire locks on rows because most of the operations that we do are row-based. You're reading a particular row or you're updating a particular row and so on. So locking individual rows is very common. The next level is the attribute level. Within each row, you have multiple attributes. This is very rare. Most systems do not provide locks on individual attributes within the row. And like I was saying, given this hierarchy, if we lock an object at some level, it automatically means locking everything under that object. So if you lock a table, you're already locking all the pages, all the rows, all the attributes inside this table. If you lock the database, this locks pretty much everything under it. This is useful because then you don't have to request individual locks on each item. If you know that you're doing something that touches many objects, you can just request the lock on the parent level. Okay, now a related topic is called intent locking. Before we go into that, let's consider this example and see how we would handle that given the information that we've just talked about. Let's say we have two transactions, right? T1 wants to scan all the rows in a given table and then update one of these rows. T2 wants to read just a single row in that table. So assuming this is the table that we're talking about, T1 wants again to scan everything and then update one row. So one way to do that would be to request S locks on all the rows in the table because it needs to scan them. And then one of these rows will get upgraded to an X lock when it wants to update this table. This is for T1. And then T2, because it just needs to read a single row, it will just request an S lock on that row. If that row happens to be one of the other rows that's being read, so S lock and S lock are compatible, then T2 will be able to acquire that and go through. If that row happens to be the same one that T1 is updating, then T2 obviously will have to wait. But if we assume that they're different rows, then both transactions can go through in this case. Of course, as we've already discussed, the problem with this particular option is that there are too many locks being requested, which is pretty expensive. The alternative, given what we talked about in terms of hierarchical locking, is that T1, instead of requesting locks on the individual rows, it could request an X lock on the table as a whole. Why an X lock and not an S lock? Because it needs to do both reads and writes. Like it needs to scan all the table and also it needs to update one row in the table, so it needs to do an X lock in this case. Of course, the problem here is that if T2 wants to read a row, then it needs to request an S lock on that row, but S lock and X lock are not compatible, so T2 will have to wait until the lock is released by T1 so that then it can proceed. So this doesn't have the problem of too many locks, but it has the problem of bad concurrency, the fact that T1 will just block the whole table and T2 needs to wait for that to happen. Those two scenarios kind of like tell us that maybe S locks and X locks are not sufficient. We need other types of locking. We need something that will indicate, for example, for T1, something that is similar to what we did in the second option, to lock the whole table for reading, and also to indicate that one of the rows needs to be updated. So basically, it's almost like we want an S lock for the whole table, but then we want an X lock for one row. Basically, we want locks that have like multi-level semantics, right? Which we don't have for X locks and S locks. This is where intent locks come in. And intent lock is basically, it's a lock that is acquired at a higher level of the hierarchy, but it also allows the transaction to acquire lower level locks at on lower level objects. What does that mean? That's super unclear. Let's look at the types of the intent locks, and then we'll explain what that earlier statement meant. So far, we've talked about S locks and X locks. So now we're going to introduce a bunch of new types of locks. First is called IS lock, or intent shared lock. The intent shared lock is similar to the S lock. Basically, this is, let's just for simplicity, let's consider two levels of the hierarchy, right? Just consider like table level and row level. So say that you want to read some rows, you have to request an IS lock at the table level to allow the transaction to request S lock at the row level. Similarly, we have IX lock, intent exclusive. So you would request an IX lock at the table level so that you can require or request X lock at the row level. We're only dealing with this because we have multiple levels of locking now, right? Like if we had only a single level of locking, then S and X should be enough. Those two are somewhat intuitive. We have another one that is somewhat different, which is called SIX lock, or SIX lock for short. Basically, it's shared plus intent exclusive lock. This is basically similar to the example that we're talking about. If a transaction wants to read the whole table and then update single row or multiple rows, then it can request this ISX lock at the top. This basically, it's like an actual S lock, but with an intent to request an X lock at a lower level. One thing to note is that the database system is the one that decides and manages all the intent locks. This is not something that the programmer explicitly decides. This is something that the database kind of like figures out based on the operations in the transaction, what objects you're trying to lock, and so on. Then it will decide whether to request something at the top level or not, and what kind of locks it will choose. So given that we are talking now about more locks than we've seen before, we need again to look at the compatibility matrix. Previously, our matrix was simple. We only had X locks and S locks, and this is what it looked like. Now we have three more types of locks to consider. So we have to expand our matrix. Basically, with 5 types of locks now, we have this new matrix. Of course, we don't have to memorize this. You can easily look this up whenever we need to. So with that in mind, just keep in mind that like if a combination is compatible, again, like on the left side, this is what a transaction currently holds, and then on the top, this is what another transaction is requesting. So if it's compatible, it means that the requesting transaction will be able to go through and acquire the lock. If they're not compatible, this means that the requesting transaction will be blocked until the lock is released. So with that, let's go back to the example that we have seen before. Again, T1 wants to scan all the table and then update a single row. T2 wants to read a single row. So with the new types of locks that we've just discussed, what can happen is T1 would request a 6 lock at the top level, at the table level. This indicates that it can read everything in the table, and that it will also request an X lock at a lower level, which is exactly what it will do. So this is for T1. Now T2 wants to read a single row. So basically, in the past we would say that it wants to request an S lock on the row that it wants to read, but for that to happen, it needs to request an IS lock at the table level. So intent shared lock. So first of all, look at the compatibility matrix. Is that compatible with the SIX lock or not? Yes, they are. So then T2 can proceed, and it will request the S lock at the row level. So this way, both transactions are able to proceed, and we don't need to request too many locks. Let's see another example. Here, T1 just wants to read a single row. T2 wants to update a single row that is different from the one that T1 is reading. So here again, T1 will request IS lock at the table level and then S lock at the row level. T2 will request IX lock at the table level. And again, look at the matrix. IX request is compatible with a held IS lock. So T2 can proceed normally, and then it will request the X lock on the row that it wants to update. So again, it did not have to do anything, or it didn't have to wait. It didn't have to request an X lock at the table level. So this is how things work. Let's look at the third example. Here, T1 is the same as the first example. It wants to scan the whole table and then update a single row. T2 wants to just scan the whole table, so read every row in the table. So T1 is going to do the same thing we've seen before. It requests a 6 lock at the top and then requests an X lock on the row that it wants to update. Now T2 wants to scan the whole table, not just a single row. So instead of requesting S locks on every row, it actually wants to request an S lock at the table level, right? Not an IS lock, it's actually S lock. So based on the matrix, S lock is not compatible with the SIX lock. So now T2 has to be blocked and wait until the lock is released. So T2 will wait. T1 will proceed until it's done, then it will release its locks. And now T2 can acquire the S lock and proceed normally. So this is how intent locks work and how they facilitate locking when we have multiple potential levels of locks. The last thing I wanted to talk about today is explicit locking. One thing I mentioned before is that locks, normally you don't need to explicitly specify what to lock, which objects to lock, and so on. This is usually something that the database will decide. But many systems provide the ability for the programmer to explicitly request locks on certain objects. This is usually not recommended for the average user because you might actually mess up how the database system works, and you might introduce like more overhead or even cause some deadlocks. So this is kind of like something just for the power user who really knows what they're doing. And this is more, you can think of it as a hint that's forcing certain behavior other than the default what the database is doing. So again, typically not everyone will use these tools, but they're there and most database systems provide them. Most of the time they give the ability to lock tables or individual rows. So let's look at some of the examples. So if we look at MySQL, for example, it has some table level locking ability using the lock table or lock tables statements and then unlock tables. This is not part of the SQL standard, by the way. This is like additional commands that are specific to MySQL. Each system may have its own commands. Some of them might be similar, some of them might be very different. We're going to look at a couple of them today, but other systems may have similar or different commands as well. In MySQL, the locks are read or write locks. This is basically corresponds to shared and exclusive locks like we've talked about last time. So you could say lock table customers read. So this basically is putting a shared lock on the customers table. So anyone else trying to read it might go through. If someone else trying to update it at the same time, then that will have to wait. You might specify locks on different tables in the same command, and then you can unlock the tables whenever you're done using them. It also provides row level locking by adding, an additional part to select statements. So you can say select, blah, 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 and then for share. This means that you're adding a shared lock to the rows returned by the select statement. So whatever rows are returned now have a shared lock on them. So if another transaction is trying to access them, let's say to update some of them, it will have to wait. You can also put an exclusive lock using for update. So basically, again, the rows returned from the select statement will now be locked for update, meaning they have an exclusive lock. So that same transaction can make changes to them, but another transactions will not be able to read them or update them at the same time until this transaction commits. Postgres has similar capabilities, but it actually has way more options. So for example, table level locking, it also uses a lock table statement, but there are many different lock modes that you can specify here, not just two. I will not go into the details, but just know like the default ones or the simple ones are the share and the exclusive. These are the same ones that we've talked about before, but there are many other lock types here that you can use. Similarly, for row level locking, you can also again do select statements and then say for share or for update, but it also has more modes here. You can say for key share or for no key update. I'm not going to get into the details of what each of these types mean for both table level and row level locking. But if you are interested, you can go to the link that I added here. It has the explanation of what each type means and also the compatibility matrices between the different types of locks, so you can know which ones are compatible with which ones. This is all I wanted to talk about today. This basically concludes our locking topic. So let's summarize. Today we continue talking about concurrency control, specifically locking. We talked about deadlocks, what they mean, how they can happen, and how we can deal with them, either using deadlock detection or deadlock prevention. We also talked about lock hierarchy. We talked about the different levels at which you can request locks, typically, which saves the cost of having to request too many locks on individual objects. We also talked about intent locking, which is a way to request lock at a higher level, which then enables the transaction to request individual locks at lower level objects. And we've seen 3 different types of locks being used in this context. And then finally, we talked about explicit locking that is provided by some of the database systems to allow the developer to request locking certain tables or certain rows explicitly rather than just rely on the database system to make those decisions. Hopefully this was useful and made locking easier to understand. As usual, please let me know if there's any question or comment or something that needs to be clarified further. Please put it in the comments and I will try to get to it as fast as I can. If you found this video helpful, please hit the like button. That will help me a lot. Please subscribe to the channel if you have not already. And with that, thank you so much for following and thank you for watching this video, and I will see you in the next video.